On the 25th of May, 1979, America's deadliest plane crash unfolded in 31 harrowing seconds at Chicago O'Hare International Airport as an American Airlines DC-10 packed with holiday travelers rolled over and plunged into the ground just moments after takeoff. 273 people perished in an immense ball of fire and a hail of riven debris. Photographs of the plane in flight immediately revealed the proximate cause. The DC-10's left engine had fallen off the wing during the takeoff roll, an extremely rare and dramatic malfunction. But the full story would prove to be much more complex, as a series of unforeseen mechanical complications, exacerbated by the very design of the airplane, robbed the pilots of the information they needed to regain control of an airliner which, in fact, could have been saved. The story would also be that of an airline which mishandled critical maintenance procedures in order to save time and money, and of a lack of communication that concealed the warnings which could have prevented the crash. But from these manifold failures of both metal and men, hard lessons have been learned. Lessons which proved critical for the future safe development of America's aviation industry. This is the story of American Airlines Flight 191. By the time the passengers and crew boarded Flight 191 at the gate at O'Hare, the story of its destruction had already entered its final chapter. All the traps had already been set, the fate of the plane and its occupants already sealed. The story, in fact, began years earlier and hundreds of miles away from the sprawling airport in Chicago. In the mid to late 1970s, McDonnell Douglas became aware that a set of bearings located inside the pylons, which attached the DC-10's number 1 and number 3 engines to the wings, were wearing out sooner than expected. In order to fix the problem, McDonnell Douglas issued a pair of service bulletins instructing operators to replace the bearings at their convenience. Complying with the service bulletins would require removing the pylons from the wings in order to access the bearings. The engine pylon is a relatively simple and unassuming object, several meters long and made of metal. It has almost no moving parts and exists only to hold the engine in its proper position forward of and below the wing. Engine pylons rarely require any sort of maintenance, a fact which posed an obstacle to airlines wishing to comply with McDonnell Douglas's service bulletin. Removing the engine and pylon was a complex and time-consuming task that was not part of any existing routine maintenance procedure, and the airlines were forced to find time for it while the planes were in the hangar for unrelated reasons. American Airlines, one of the largest operators of DC-10s, decided to carry out the work on the bearings when each plane went in for its C-check, a yearly session of thorough inspections and heavy maintenance during which the aircraft needed to be on the ground for an extended period. But the airline already had good reason to believe that replacing the bearings would be exceptionally arduous. In 1978, American Airlines performed contract work on several DC-10s on behalf of a foreign carrier, which had asked them to bring the planes into compliance with the 2 McDonnell Douglas service bulletins concerning the pylon bearings. The manufacturer's recommended procedure called for mechanics to first remove the engine from the pylon, then remove the pylon from the wing, a requirement which American Airlines felt was unrealistic because it took hundreds of man-hours and involved the removal of no less than 79 different connections. On the other hand, if the engine and pylon could be removed together as a single unit, then the process involved only 27 connection points, saving nearly 200 man-hours of labor. Engineers at American were already aware that United Airlines had used this method to drastically reduce the time and effort involved in complying with the service bulletins. But while United used an overhead hoist to raise and lower the engine and pylon, American Airlines opted for something even cheaper and easier: a forklift. The tricky part of raising and lowering the engine pylon assembly using a forklift was that the 2 parts together weighed more than 8,100 kilograms, or 18,000 pounds, and even the most skillful forklift operator could only adjust the height of the forks in increments of 6 millimeters, or 0.25 inches. To make matters even worse, the center of gravity of the engine pylon assembly lay nearly 3 meters forward of the pylon's forwardmost attachment points. All these factors meant that the process of detaching the pylon and engine, lowering them to the floor with the forklift, and then raising them back up to reattach them, had to be performed with the utmost care. One slight miscalculation of the center of gravity, one tiny shift of the forks, and 8,100 kilograms of metal could slam into the underside of the wing. American Airlines managed to carry out this procedure on the foreign airplanes without causing any damage. However, its maintenance engineers found that it was easier to do the work if some of the steps were performed out of order. The pylon is basically connected to the wing by 3 sets of attachment points, 2 at the front and 1 at the rear. The original procedure for detaching the pylon asked mechanics to remove the front attachments first. But with the engine still attached to the pylon, the stress on the forward attachment points was too great to remove the pins, and the problem could only be alleviated by disconnecting the rear attachment point first. While this made the pylon easier to remove, it also turned the forward attachment points into a rudimentary hinge. If the forks were lowered too much following the removal of the aft attachment point, the heavy engine would cause the entire unit to rotate around the forward attachment points, sending the aft end of the pylon slamming upward into the underside of the wing with a force of more than 9,000 kilograms, or 20,000 pounds. Despite the risks involved in this procedure and the difficulties that mechanics experienced while trying to carry it out, the airline was still using the same method when the DC-10 registered N110AA came in for its annual C-check in March 1979. At the American Airlines maintenance base in Tulsa, Oklahoma, engineers set about bringing the plane into compliance with the manufacturer's service bulletins, including those related to the pylon bearings. As they had done several times before, they positioned the forklift beneath the engine's center of gravity, removed the attachments, lowered the assembly to the ground, carried out the repairs, gave it a cursory inspection, and finally prepared for the trickiest part of all, putting the pylon back into its mountings. At some point during the process of reinstalling N110AA's left engine pylon assembly, the pylon shifted and struck the bottom of the wing. When and how this happened is not known with certainty, but it might have occurred during a shift change or when the forklift ran out of fuel and briefly sat idle. This forklift was known to bleed hydraulic pressure, and the forks would drop by about 2.5 centimeters every 30 minutes when the engine was off, easily enough to shift the engine pylon unit around the forward attachment points and push the rear end of the pylon up into the wing. When the pylon collides with the wing in this manner, the brunt of the collision is absorbed by the pylon's aft bulkhead. The bulkhead, a stiff metal plate spanning the interior cross-section of the pylon, normally attaches to a clevis on the bottom of the wing. But removing this connection was the first thing the mechanics did when they started disconnecting the pylon, and the last thing they would do when putting it back together. Without the bolt joining the bulkhead to the clevis, the bulkhead could be forced farther upward until the clevis impacted the upper flange of the bulkhead. On N110AA, this impact severely dented the upper flange and created a 25-centimeter crack right across the top of the bulkhead. Incredibly, no one noticed. No one heard the sound of the impact over the general hubbub inside the hangar, and inspectors didn't spot the crack because it occurred after the inspection was completed. The mechanics screwed the pylon back in place and went home, completely unaware that the internal structure of the pylon had been fatally compromised. With a 25-centimeter crack through the aft bulkhead, the remaining life of the pylon could be measured in weeks. Every time N110AA took off, thrust loads passed through the weakened bulkhead, resulting in rapid metal fatigue. The crack grew steadily over the next 2 months, creeping outward in both directions until it reached a length of 33 centimeters. At this point, the entire pylon was hanging by a thread. One more load cycle and it would fail. That final load cycle turned out to be American Airlines Flight 191 on the 25th of May, 1979. 258 passengers and 13 crew boarded the plane, strapped themselves in, and prepared for the 3.5-hour flight to Los Angeles. Little did they know that Flight 191 would barely even make it past the end of the runway. In command that day was 53-year-old Captain Walter Lux, a veteran pilot who was type-rated on at least 8 different airliners and had more than 22,500 flight hours under his belt. Assisting him were 49-year-old First Officer James Dillard and 56-year-old flight engineer Alfred Udovich, who together possessed an additional 24,000 flight hours. Their experience alone would have gotten them out of many sticky situations, but unfortunately, not this one. At 15:02 that afternoon, the O'Hare Tower controller cleared Flight 191 for takeoff on runway 32 right. "American 191 underway," Captain Lux replied. It would be the last time they spoke to air traffic control. With First Officer Dillard at the controls, the DC-10 thundered away down the runway, powered by its 3 big General Electric CF66 turbofan engines. They hit 100 knots, then passed through V1, decision speed, and continued onward to VR, rotation speed. Lux called out, "Rotate," and Dillard pulled back on his control column to lift the plane off the runway. It was at precisely that moment that disaster struck. Unable to withstand the takeoff load, the damaged pylon aft bulkhead split into several pieces, ripping out the aft connection points. Held to the wing only by the forward attachment pins, the entire number 1 engine and pylon unit started to rotate as the engine thrust propelled it forward and upward. In the blink of an eye, the engine folded back over the top of the wing and fell away behind the plane, tumbling down the runway in a shower of sparks. Inside the cockpit, Captain Lux uttered the word "damn," and then the voice recorder went dead. From the tower, controllers watched in amazement as Flight 191 lifted off from runway 32R, with its left engine completely missing. "Look at this! Look at this!" a controller exclaimed. "He blew up an engine! Equipment! We need equipment! He blew an engine!" The DC-10 climbed in a level attitude for 15 or 20 seconds. Then it started to bank to the left. "American 191 Heavy, you want to come back, and to what runway?" the tower controller asked. There was no reply. "He's not talking to me," the controller said to someone in the tower. As controllers, pilots, and hundreds of travelers watched in stunned disbelief, the DC-10 kept banking left until it was flying on its side, streaking past the end of the runway at a height of 300 feet, with hydraulic fluid streaming from the damaged left wing. Within seconds, the plane started to turn inverted. "Yeah, he's gonna lose a wing," said one of the controllers. There he goes, someone exclaimed. With a tremendous boom and an earth-shaking roar, American Airlines Flight 191 slammed into an open field 1,600 meters beyond the end of runway 32R, angled 21 degrees nose down, and banked 112 degrees to the left. The plane shattered instantly into thousands of pieces, sending a wave of disintegrating debris tearing through an aircraft parts warehouse, several Quonset huts, an auto repair shop, and a junkyard before coming to rest at the edge of a mobile home park. A huge fireball, visible from the terminal at O'Hare, unfurled into the bright blue sky as the plane's full load of jet fuel ignited. In the mobile home park and the nearby warehouses, people ran for their lives, fleeing what one witness later called a rain of fire falling. As firefighters hurried to the scene of the crash, they already feared that no one could possibly have survived the horrific impact. When they arrived, those fears were sadly confirmed. The largest remaining piece of the plane was one of the badly mangled engines. Everything else had been reduced to charred rubble, scattered through the field and smeared across the burning facades of the warehouses, where the hulks of cars lay tossed about within a sea of flame. Unfortunately, save for two badly burned employees of Courtney Velo Excavating, a company operating out of one of the warehouses, rescuers found no one to save. In fact, there wasn't a single whole human body. It was obvious that all 271 passengers and crew aboard Flight 191 had died instantly when the plane struck the ground. It would be several days before recovery crews found the bodies of two more people who died on the ground. A truck driver for Courtney Velo found still in the cab of his truck, and Andy Green of Andy's Auto Service found underneath the car he was working on when the fireball tore his shop asunder. With 273 people dead, the crash was by far the worst aircraft accident to occur on U.S. soil. A grim title which it still holds today, 45 years later. But the DC-10, like all airliners, is capable of climbing normally after losing an engine. To explain how the loss of the #1 engine could have led to a catastrophic crash, investigators needed to look at the effect of the failure on other aircraft systems. The most immediate consequence of the engine separation, apart from the loss of thrust, was the uncommanded retraction of the outboard left wing slats. The slats are panels which can slide out of the leading edge of the wing to increase its capability to generate lift, enabling flight at lower speeds during takeoff and landing. On the DC-10, the slats were held in the extended position for takeoff by hydraulic actuators, but the separation of the engine severed the hydraulic lines connecting the slat control valves for the outboard left wing slats to their associated actuators. With no local hydraulic pressure to hold them in the extended position, aerodynamic forces overcame the actuators and forced the slats to retract. When the left wing outboard slats retracted, the other slats did not retract, creating an asymmetric lift condition. Calculations showed that with the outboard slats retracted and the engine missing, the left wing would cease to generate lift below a speed of 159 knots. This was the wing's stall speed, the speed at which the angle of attack, the angle of the wing relative to the airstream, reached the critical point. At this critical point, airflow separates from the wing and becomes turbulent and disorganized, leading to a catastrophic loss of lift. As it turned out, the pilots would have run right into this critical airspeed simply by following established procedures. The checklist for an engine failure on takeoff instructed pilots to climb out at V2, takeoff safety speed, until reaching 800 feet, then lower nose and accelerate. The checklist told pilots to use their calculated V2 speed because it was a known value already designed to ensure stable flight following an engine failure. But on Flight 191, V2 was 153 knots, lower than the 159 knots at which the left wing would stall. By following the checklist and letting their speed drop to V2, the pilots unknowingly doomed their plane and everyone on it. Indeed, the flight data recorder revealed that Flight 191 began turning to the left as soon as it decelerated below 159 knots. At that point, the left wing stalled and lost lift, while the right wing, which still had all its slats extended, continued flying, resulting in a left roll. The pilots attempted to turn right using the rudder and ailerons, but these controls would have been useless if the left wing wasn't generating lift. At the moment of impact, Captain Lux and First Officer Dillard were applying full right rudder, full right aileron, and full nose-up elevator inputs, but their efforts were in vain. To recover control, they would have needed to push the nose down until their speed rose back above 159 knots, at which point the plane would have rolled out of the turn without difficulty. So why didn't they do this? One possibility was that a hydraulic failure robbed them of their ability to manipulate the controls. But while hydraulic fluid was seen spewing from the wing, the flight was too short for any of the hydraulic systems to have suffered an appreciable loss of pressure due to this leakage. Indeed, all the flight controls were working right up until impact. As it turned out, the reason why the pilots couldn't regain control of their stricken plane didn't have to do with the hydraulics, but with the design of the DC-10's electrical system. Like all airliners, the DC-10's engines generate electricity to supply the aircraft's electrical system. When an engine fails, so does its generator, and the associated AC generator bus will lose power. If such a failure is detected, a device called the AC tie bus will activate to tie the failed AC generator bus to one of the other generators, restoring power to systems which rely on the failed generator. But if a fault is detected with the AC generator bus itself, a circuit called the bus tie relay will open instead, isolating the failed bus from the AC tie bus and preventing an electrical malfunction from spreading to the rest of the system. This was what occurred on Flight 191. As the engine broke away from the wing, numerous wires were severed, creating transient short circuits which tripped the bus tie relay and isolated the number 1 AC generator bus. This bus powered a number of aircraft systems, including the cockpit voice recorder, explaining why the recording stopped at the moment of the failure, as well as all the captain's instruments, the slat position computer, and the captain's stick shaker stall warning. The failure of these systems directly led to the pilot's inability to recover control. Because of the failure of the slat position computer, the slat position indicators in the cockpit went blank, and the slat disagree warning, which would have informed the pilots that some of the slats had retracted, never went off. Therefore, the pilots could not possibly have known that they had a slat asymmetry problem. As far as they knew, all the slats were still extended. The second nail in their coffin was the failure of the captain's stick shaker. At the time, it was not required that both pilots' control columns be equipped with stick shaker stall warnings, and only the captain's side had one. A stick shaker for the first officer, which would have received power from a different electrical bus, was sold as an optional extra, but American Airlines had opted not to buy it. As a result, the stick shaker never activated, and without the slat disagree warning to tell them about the partial retraction of the slats, the pilots would have assumed that the plane would stall at the slat's extended stall speed, which was comfortably below V2. The cumulative effect of these failed warnings was that the pilots never realized that they were in a stall, nor could they reasonably have concluded this from the indications which were available to them. However, while it is widely believed that the presence of a second stick shaker would have allowed the pilots to detect the stall and save the plane, this is not actually true. The DC-10's stall warning computers only received slat position data from their own side of the airplane. There was no crossover. Because the slats only retracted on the captain's side, the first officer's hypothetical stall warning computer would not have known that any of the slats were retracted, and consequently his stick shaker wouldn't have activated until the plane reached the slats, extended stall speed. This speed was much lower than the speed at which the stall actually occurred, and in fact the plane never decelerated enough to reach it. Only by restoring power to the slat position computer and the captain's stick shaker could the crew have received a stall warning at the correct speed. The only way to have restored power to these failed systems would have been for flight engineer Udovich to manually reconnect the number 1 AC generator bus by flipping the emergency power switch. However, this switch was located not at the flight engineer's station, but on the overhead panel above the pilots. Even if he had recognized the need to activate it, a very big if, he would have needed to get out of his seat, walk across the cockpit, and flip the switch, all in the middle of an extremely dynamic emergency in which multiple critical systems were failing. Investigators felt that he could not reasonably have been expected to do this during the 20 seconds or so before the plane went out of control. A series of simulator tests proved that the failure of the warnings was causal to the accident. After being briefed on the nature of the emergency, pilots who faced a simulated engine separation and partial slat retraction were easily able to maintain control and come around for an emergency landing. However, they universally agreed that without the warnings, no pilot could have understood the situation quickly enough to prevent the crash. Because of these findings, the NTSB heavily criticized several aspects of the design of the DC-10, which featured an unacceptable lack of redundancy. The lack of a stick shaker for the first officer, while not uncommon at the time, was a relic of an era when the captain was the supreme authority in the cockpit, a belief which by 1979 was already on the way out the door. Investigators felt that the first officer's stick shaker should have come standard rather than being sold as an optional extra, even though this was not technically required. Secondly, many other airplanes had mechanical locks to prevent the slats from retracting in the event of a hydraulic failure, but the DC-10 did not. Additionally, good design principles hold that warnings should have backup sources of power and data so that they don't fall silent at the moment of greatest need. And finally, designing the stall warning systems to only take slat position data from one wing rather than both was quite simply a lazy design. It is not hard to provide data crossover, and the safety benefits are significant. Most likely, McDonnell Douglas designed such a crude stall warning system because the DC-10 had a perfectly good natural stall warning in the form of severe pre-stall buffet. A stick shaker was only required because of a couple of edge cases where the buffet wouldn't give warning far enough in advance, and Douglas likely viewed the stick shaker primarily as a means of fulfilling regulatory requirements rather than a system which was critical to the safety of the airplane. Unfortunately, in this case, it was safety critical because the stall experienced by Flight 191 resulted in little to no pre-stall buffeting. Despite the criticism levied at McDonnell Douglas, the party most clearly responsible for the crash was American Airlines. The crack in the left engine pylon's aft bulkhead occurred because of the airline's practice of removing the engine and pylon as a single unit using a forklift. Although it was faster, this process was imprecise, finicky, and prone to errors. In fact, before performing the procedure for the first time, American Airlines maintenance supervisors had asked a McDonnell Douglas engineer whether it was all right to remove the engine and pylon together, and the engineer told them not to do it. However, McDonnell Douglas didn't have the authority to police the way airlines were maintaining its planes, and American Airlines ultimately decided to go against the manufacturer's advice. The labor costs, which could be recouped by using the shortcut, were simply too good to pass up. In the immediate aftermath of the Flight 191 disaster, as it became clear that cracks in the pylon had caused the crash, authorities finally took action. 3 days after the accident, the FAA ordered emergency inspections of the engine pylons of all DC-10s in the United States. To the horror of all involved, the inspections found cracks in the pylon aft bulkheads of 6 more DC-10s, 2 at Continental and 4 at American Airlines. One of these cracked bulkheads was experiencing metal fatigue and probably would have failed eventually, causing another accident had it not been caught. In light of these findings, on June 6, 1979, the FAA ordered the grounding of every DC-10 in America, until such time as it can be ascertained that the DC-10 aircraft meets certification criteria. The DC-10s remained grounded for more than a month until the FAA rescinded the order on July 13th, citing the fact that the cracks were the result of a particular unsafe maintenance practice rather than a design flaw with the airplane. The planes flew again a few days later, now under the protection of an FAA directive, which declared any DC-10 legally unairworthy if the engine and pylon were removed as a single unit.